Hey guys, this is the Chem 1 lecture on half reactions and electrochemistry. We're going to be learning how to write half reactions involving reduction and oxidation, and we'll be visually showing the gain or the loss of the electrons in the reaction. So how do you write a half reaction? The first thing you do is you're going to want to pair up like elements. Doesn't matter which one you write first, I just usually start with the first one given. So my first half reaction is going to involve copper as a metal, turning into a copper plus 2 ion. And then my other pair is I have 2 silver ions, producing 2 solid silver. So I've split it into halves, and we want to identify which one is being oxidized, which one's being reduced. So you're going to want to maybe remember the acronym OIL RIG. Oxidation is loss, reduction is gain. So if we look at copper, remember elements not in a bond have an oxidation state of 0. So for our first reaction, copper went from 0 up to plus 2. So it got more positive. You can get more positive by losing electrons. So copper was oxidized. And then silver was at plus 1, and it went down to 0, so it must have gained some electrons. So therefore, trouble. And then the last thing we have to do is show the electrons that are actually being gained or lost. So once you've identified, for like example, the first one that's being oxidized, so we know that it's losing electrons, anytime that we are losing electrons, electrons are going to be placed on the product side. So it kind of shows, if you're reading left to right, they're being lost from the reaction. Kind of like exothermic, like heat was always on the product side if it was exothermic. And then therefore, if the reaction is gaining electrons, you're always going to see electrons on that reactant side. Okay, so now how did I know to put 2 electrons on the right and the left? So when you are writing half reactions, you want the overall charge of the reactants and the products to be the same charge. They don't have to be 0 on both sides, but they just have to be the same number. So we started with copper having a 0 charge on the left and a plus 2 charge on the right. And then what we're bringing in are electrons, and electrons have that negative charge. And so you'll learn the pattern is you always want to go to your more positive side. That's going to help you balance the charges. And so because that left side was 0, if I bring in 2 negatives, plus 2, negative 2, changes my overall charge to 0, which matches that left side. Same thing on that bottom one, we have an overall plus 2, so you do have to account for that you have 2 silver ions. So this was originally a plus 2 charge. This side was 0 because silver was a solid. We want the charges to be the same. We only have negatives to add, so we brought in 2 negatives to balance off the 2 positives, therefore creating a 0 charge on the left, matching the 0 charge on the right. Okay, let's try another example. Writing half reactions, you start by pairing up like terms. So we have bromine going to a bromine ion. We have an iodine ion going back to its element of iodine. Identify which one's being oxidized, which one's being reduced. Bromine started at 0, went down to negative 1. So we saw a reduction in its charge. Iodine went from negative 1 up to 0, so we saw an oxidation. Then we got to plug in the electrons. So we know reduction is the gain of electrons. And we just have to figure out how many electrons are we adding on this left side. Well, what does our 2 sides equal? So the right side currently has a negative 2 charge, and the left side's currently at 0. So your more positive side is the 0 side, because remember, the only thing we can bring in are negatives. Looks like we'll need to bring in 2 negative electrons. So bromine literally gains those 2 negative electrons and becomes that bromine ion. For your oxidation number, this side's currently negative 2, this side's currently 0. So look at your more positive side to add in the electrons. Well, if we bring in 2 electrons, now we have a negative 2 charge on both sides. And so we're seeing that oxidation loses 2 electrons, which are then gained by that bromine ion. Okay, so here's what it looks like without all of the markings everywhere. We should always have electrons on opposite sides. One of them has to be losing electrons, one of them has to be gaining electrons in order for it to be a redox reaction. They're complementary. You can't have one without the other. Okay, we're going to go through these next two fairly quick. So on this third example, I've already gone ahead and done everything. I had paired up aluminum, and it's oxidized because the charge went more positive in the reaction, and then the lead ion was reduced. It went from +2 down to 0. This one you had to be careful just to make sure you multiply the charges. So 2 times 3 gave this side an overall +6, versus the other side was 0. We always want the charges to be the same number, and we brought in electrons, and so we need to bring in 6 negatives so that our charge got knocked down on the overall side to 0. And then same thing, we had a +6 and a 0 side, so we added 6 electrons in the reduction line. So lead-2 ions, 3 lead-2 ions will absorb or gain those 6 electrons to have 3 solid lead. And here's the last example worked out. We saw that zinc was oxidized, it went up in charge. Copper was reduced, it went down in charge. I added 2 electrons so that +2 and -2 would balance this side to 0. Zinc was already at 0. And then copper had a +2 charge on this side and a 0 charge, so I added in 2 electrons. That fits because oxidation shows the losing of electrons, with electrons being on that product side. And this showed the gain of electrons, and that's what reduction is. So sometimes we'll give you the full chemical reaction, like this is a single replacement reaction, instead of already giving you what's just the things that are being oxidized and reduced. And so you have to then first determine who's being oxidized and reduced, and you do that by assigning oxidation numbers. So we know any element, sorry, that number went a little crazy. Any element that is not in a bond has an oxidation state of 0. And then if they're in a bond, you need to consult your oxidation rules. And then evaluate, did anybody not change charges? We would call those spectator ions. And it would appear that chlorine stayed -1 on both sides of the reaction. And now we're kind of starting with where we've been. And remember, the goal is to write a half reaction. So we have sodium, 2 sodiums that are elements becoming ions, and then we have magnesium ions becoming solid magnesium. Identify who's been oxidized, who's been reduced. Sodium started at 0, went up to +1, so it was oxidized. Magnesium started at +2 and went down to 0, so it was reduced. And then lastly, add in the electrons. This current side is a +2 side, and this current side is 0. So I will be adding in 2 electrons here, which makes sense because 2 electrons must have been lost. Reduction, so this side's currently at a +2, this side's at 0. I will add in 2 electrons on that reactant side because reduction is magnesium ions are going to gain those electrons. Okay, one more thing before we actually get into electricity is we could have you go backwards. We can give you the 2 half reactions and you combine it back to the overall reaction. Here's going to be the key. The number of electrons have to be balanced. And that's because in a redox reaction it's complementary. However many electrons are lost are the amount gained. They can't be uneven. So if you find yourself in like number 1, where it shows 1 electron being gained but 2 electrons being lost, you're going to have to do a multiplier where you can multiply whatever half reaction. Maybe only one part of the reaction has to be adjusted, but in the end the electrons must cancel out. So for this one, 1 and 2, like basically we'll go like least common denominator, which would be 2. So I could double my half reaction to create 2 electrons, and that also gives me 2 lithium ions, 2 solid lithiums, but then my electrons would cancel out. An overall reaction, kind of like back in Unit 15, when you're combining like mechanisms, like multiple steps, you then write write everything that didn't cancel out, but you have to account for the multiplier. So now we have 2 lithium ions plus copper, so I'm gathering up everything on the left. And then on the right side, I have 2 lithium and a copper 2 ion. You know you've done it right when your electrons cancel out. And then you can always check yourself. 2 lithiums, 1 copper, 1 copper. My overall charge over here is +2. My overall charge over here is +2. Okay, let's try example number 2. So I notice I have 2 electrons and 3 electrons. Those are not the same number. So let's go least common denominator. In this case would be 6. So I want them to equal the number 6. So the top is going to have to get multiplied by 2. And the bottom is going to have to be multiplied by 3 in order for my electrons to cancel out. So I'm going to have 2 aluminums on the left plus 3 magnesium ions. And then on the right, I'm going to have 2 aluminum ions plus 3 magnesium atoms. It's easy to forget your multipliers, but just like when you multiply the top by 2, then wherever there's aluminum, there should be a 2 in front of it. And the bottom, we multiplied by 3, so just make sure that there's a 3 in front of your magnesiums. And now you've gone back to the overall reaction. Okay, this next part of our lesson is another application of redox reactions. So we've talked about redox reactions with rusting or tarnishing and those and in photosynthesis. But another place where you see redox reactions is with electricity from chemical reactions. And so remember, redox reaction, electrons are being lost, electrons are being gained, and energy is released sometimes in the form of electricity. So the energy is converted from chemical energy to electrical energy, literally producing electricity or the movement of electrons. And so 2 examples I have that I think are cool, they're not in your notes, are fireflies or even like fish in like the deep sea that have these luminescent, these lights from within. That's because a redox reaction is happening in their body. So electrons are being lost, electrons are being gained, and that energy is getting transformed into light. And so when we see fireflies and they're illuminating, that's coming from a chemical reaction. And another one is on a crime scene, they use a substance called luminol, and when luminol reacts with iron, it's a redox reaction that produces a glow. This is my awesome light bulb over here. And so how does that relate to a crime scene? Well, there is iron in our blood. And so if they're at a crime scene and they're not able to see with the eye if there's any blood splatter or blood in there, when they spray luminol around the scene, if there is any blood that has iron in it, these 2 things will react in a redox reaction and will produce light that we're able to see with our eye, and that can let them see patterns or wherever it might be. So I think this is a really cool application of redox reactions. You'll go a lot more with electricity in physics, but we're just going to look a little bit at this idea of flow of electrons. And the main unit we're going to be using is voltage, which is just the energy associated with this flow of charges. So every half reaction has a certain amount of energy or volts associated with it. You're going to see the symbol E naught, and the units are volts, so how much energy associated with it. Hydrogen has been arbitrarily decided as the standard, and so you're going to see hydrogen at 0. And then anytime you see a half reaction with a positive value or just there's no sign, those are substances with positive voltages. So they will produce electricity when that type of half reaction happens. If you see a negative voltage sign, then that means it typically doesn't like to do that direction. So like here you have iron plus 3 being reduced to iron and there's a negative voltage associated with it, this won't happen easily. So negative signs mean they don't really prefer that direction. So everybody should have this list, and you would be given this on a test as well. It's mainly knowing how to read it. Notice this is called the standard reduction potential. So every one is written with going down in charge, but we know that we're dealing with redox reactions. So why don't we have an oxidation chart? Well, that's because we can just simply flip the sign of the redox potential to get our oxidation potential. So for example, at the top, lithium is being reduced and there's that negative voltage associated with it. Well, if we wanted to literally reverse this and have lithium oxidized, we would simply flip the sign. So if it's negative, it becomes positive, and if it's positive, it becomes negative. So with an idea, like anything that's negative, they actually would prefer the opposite of reduction. They would prefer to be more oxidized. And then if they're positive, they like the direction they're already in, which means they're being reduced. So now we're going to start evaluating half reactions with their voltages and getting to add up voltages of half reactions. And so if you have two half reactions that add up to a positive voltage, this is called a spontaneous reaction. Like they will, without any help, produce electricity. But if your redox reaction, the voltage potentials add up to a negative, this is a non-spontaneous reaction. It's not going to happen. It's not going to produce electricity without some outside source. So just try to keep those straight. Positive means the reaction's going to happen by itself, versus negative means it's not going to happen unless there's an outside source giving in energy. So to calculate the overall voltage, you'll still break your two half reactions up. Then you're going to have to look at the standard reduction potential. If it's being reduced, then it fits the chart as is. But for your oxidation, this is what people forget, guys, and we'll go through lots of examples, is the oxidation potential has to get flipped. Like the sign gets flipped. If it's positive, the sign becomes negative. If it's negative, the sign becomes positive. Do not, even if you have to multiply things or add more electrons, do not change the value of E. It's a set ratio. And then you just simply add the two E values up. And if they add up to be positive, you know it's spontaneous. If you add up to be negative, it is non-spontaneous. All right, so now we're going to evaluate the redox reaction and figure out the total voltage for this reaction. So we do that by first splitting up our half reactions. Zinc goes to a zinc ion. Copper 2 ion goes back to solid copper. Identify which one's being oxidized, which one's being reduced. Zinc's being oxidized because it's going up in charge. Copper's being reduced because it's going down in charge. Balance out your charges by adding or showing the loss of electrons. So this is where we've been so far in this lesson. And all we're doing now is bringing in our electricity that's associated with this each half reaction. So I like to do my reduction first because that's going to match my chart because we're looking at, it says use the standard half cell reduction potential. So I should see this identical thing. So copper plus 2, and you have to watch out that there are multiple coppers with multiple different electrons, so make sure you're really getting copper plus 2 with 2 electrons. And I'm seeing a voltage of 0.340. And then with oxidation, you're not going to see it as is, right? We're going to have to flip it. So on your chart, you're going to be actually looking for zinc plus 2 first. See it near the top. And my chart says negative 0.763, but because it's oxidation, you flip the sign. And then once you have your two E values, you add them up, and you get a total of positive 1.103 volts. And this would be a spontaneous, spell that right? Reaction. So this reaction would produce electricity without any help. All right, for the second example, I've already split my two half reactions, identified magnesium is being reduced, silver is being oxidized. I've added in my electrons, but we're not asking for an overall, so I'm not going to balance the electrons because that doesn't affect my voltage. So I want to get my potential energy for each half reaction. Remember, I personally like to start with reduction because that's what's given to me on the chart. So I'm going to look for magnesium plus 2, kind of near the top, and it has a negative 2.356 volts associated with that. And for oxidation, what do we do for oxidation on a reduction-only chart? We flip the sign. So you're not going to see it in this order. You're not going to see it being oxidized. You're probably wanting to look for Ag plus 1, which is kind of near the bottom of the sheet. And on the table, it says the reaction is, or the voltage is 0.799, but we have to flip the sign, so positive becomes negative. So we happen to have two negative potentials, which is going to add up to a big negative, negative 3.155 volts. So that was the total cell potential. And this would not work. This would be a non-spontaneous reaction. No electricity would be produced from this. Okay, we have two more examples that are fairly similar to what we just did. Break up into half the reaction. I'm going to go ahead, I think, and do that for y'all. Okay, so lithium is being oxidized because it's going up in charge, and I add 1 electron to balance my charge of 0, 0. And then iodine is being reduced because it's going from 0 down to negative 1. This whole side has that negative 2 charge, so I bring in 2 electrons on that opposite side so that that side has a negative 2 charge. Then we want to know what is the electrical potential of this redox reaction. So for me, I like to start with reduction because I don't have to flip anything. So I'm going to look for iodine. I2 looks like it's below the hydrogen, and I get to write that number as is, as 0.536. And then for lithium, if it's oxidized, that's not showing up directly on my chart. I'm going to have to flip that sign. Lithium's at the way top. It's negative 3.040, but I have to flip that sign to positive. So sometimes people write like a double negative showing that they flipped it, or you could just switch it to positive, kind of whatever your groove is going to be. Add up your two half cells. You're going to get a positive 3.576 volts, and this would be a spontaneous reaction. All right, last one, we're looking at gold, plus 3 down to 0, so it looks like gold's being reduced. Which means cadmium's hopefully being oxidized. It's starting at 0, going up to that plus 2 charge. Adding our electrons, this whole side's got a positive 6 charge going on. This side's got 0. So I'm going to add 6 electrons. And then this side, 3 times 2's got that positive 6 and 0. So this means they're losing 6 electrons. All right, then we go look at that, let's go yellow, cell potential for each half reaction. I'm going to start with reduction, looking for gold, and really be careful on those transition metals that have multiple charges, because you can see multiples on your reduction sheet. So this is Au plus 3. And it's going down to 0. So now on your sheet, I didn't see 6 electrons, and that's because your sheet is most simplified. And so then really zone in on those charges. You're going +3 down to 0. And the only way to do that is to gain 3 electrons. So that charge would be Au plus 3 electrons. I'm seeing 1.520. I don't have to flip it because it's the one being reduced. And then oxidation, so you're not going to see these balancing. You're going to see most simplified. So really 1, 1, 2. But you're looking for cadmium +2 with solid cadmium. So CD, looks like it's above hydrogen on the list. And the chart says it's negative 0.403. But we know that we'll have to flip the sign. And so this looks like it's going to come out positive, 1.923 volts. And we know when the total voltage is positive, this reaction, when it occurs, will produce electricity. That chemical energy will get converted into electrical energy. So this last example is not in your notes, so it's extra, or if you're totally spent, it's on you if you want to finish this. But what would happen if you stirred a solution of iron 2 chloride with an aluminum spoon? So I wrote out this single replacement reaction, iron 2 chloride reacting with aluminum. Aluminum is going to replace iron to make aluminum chloride and iron. Split it into its half reactions. Iron's reduced, aluminum's oxidized. Add up the potential energy, flipping the oxidized, and this is going to be a spontaneous reaction. So then what that means is that your aluminum spoon is not going to stay aluminum. There's going to be a reaction on the spoon. And so maybe you don't want to use an aluminum spoon. Maybe something like glass or plastic that won't react to the iron 2 chloride. It looks like you would actually form iron on your spoon. So we probably don't want that. But this is how you can use electrochemistry to predict what will happen to your stuff when you mix it in solution. All right, thanks guys for watching, and have a good day.